Okay, please.
So, welcome to today's seminar given by Alberto Dominguez, who did his PhD between University of Seville, the Instituto of Astrofísica de Andalucía, and the University of Santa Cruz, California, Santa Cruz. Then he spent 3 years working as a postdoc in University of Riverside in California as well, working with data from the Hubble Space Telescope, followed by another postdoc of 1 year at the University of Clemson, South Carolina. And finally, he landed in Madrid in 2015, where he is currently a Ramón y Cajal Fellow. And today, his presentation is about the topic of his PhD, which is the extragalactic background light and the consequences on galaxy.
Okay, thank you, Mireia. First of all, I want to thank the organizers for letting me present my work here. And I also want to thank the High Energy Group for kindly hosting me. It is always a pleasure to be back at the IACTS here in Tenerife. I'm going to tell you about some results from the work I've been doing during the last years. All of them are focused on trying to measure all the light in the universe. This might sound very ambitious, but you will understand in the next slides what I actually mean by this. So this topic I really like because it beautifully connects high energy astrophysics with, let's say, more traditional astronomy. And I hope I also convince you about this by the end of the talk. So the question of how bright is the universe goes back probably even before the ancient Greeks, but was written in a more modern form by the German astronomer Hendrik Olbers. This is known as the Olbers paradox, and it says, given the current cosmological framework at that time, that in an infinitely old universe, that is infinite in space and contains an infinite distribution of stars, the night sky should be bright in opposition to what we observe. So this is very simply illustrated here, where you see that given enough time, all the sky should be covered by a source light. Of course, the solution to this problem is given by the current cosmological framework. Very quickly, we know that there was this event known as the Big Bang that happened more than 13.5 gigayears ago, and it was followed by a very quick exponential expansion of the universe known as inflation. It was followed by the recombination period when the CMB was produced all at once, and it was quickly followed by star formation. We have seen galaxies already as early as a few hundred million years after the Big Bang. So galaxy formation started pretty early in the history of the universe. This star formation has been going on till our days, of course, and one of the consequences of these star formation processes is the emission of radiation. So this radiation eventually escapes galaxies and accumulates in the intergalactic space, and it is, of course, also restricted by the expansion of the universe. So all this light accumulated is what we know as the cosmic diffuse background. So this is a figure showing the spectral intensity of these cosmic backgrounds that, as you can see, go essentially they cover the whole electromagnetic spectrum, going from the very energetic gamma rays down to the low energy radiation. Of course, we see here the CMB black body spectral shape, and this type of space parameter is very, very interesting because essentially the area inside the curve in this representation give us an estimate of the energy contained in the background. So you can see that the CMB is energetically speaking the most energetic background. But we have here also this double peak shape that is what we know as the extragalactic background light, or EBL. It is a combination of an optical peak that is due to stellar emission and this other peak in the infrared that is produced by absorption and re-emission of stellar light by gas. As you can see, it is the second background, energetically speaking, in importance after the CMB. So, how do we measure this EBL? How do we measure this EBL? So, it is actually very challenging doing it directly, because you can imagine that you want to measure this extragalactic, very faint signal that we want to measure from Earth, that essentially is covered by contaminants exactly at the wavelength that we want to measure. So probably the first serious attempt of measuring the EBL directly, when I say directly, is using absolute photometry. Was done by the COVID satellite that had an instrument known as derive, that it had a field of view of about 0.7 square degrees. So this is about the size of the full moon. And derive imaged the whole sky in 10 photometric bands, okay, going from the near infrared up to the far area. Excuse me.
So easy to organize time.
Yeah.
Just go talking.
Okay, thank you. So these are 3 examples of these results in 3 different bands. So of course, this is a sky map represented in galactic coordinates. So what we see here is the plane of our own galaxy. Okay, so the methodology is scanning the whole sky with photometry and have an estimate of what are the contributions to that total signal that you are measuring with your instrument. So this is just for illustration purposes. This is a table that tells you how much light measured did we in these units at this wavelength. The total isotropic signal that it was found was this. You can see that zodiacal light, that is the main contaminant. It is even visible with the naked eye, so it is something really strong. You need to remove zodiacal light, the brightness of the interstellar medium. You need to remove the bright and faint stars of our own galaxy. And what remains is this EBL. The EBL is an order of magnitude lower than the foregrounds, and of course, due to these problems in subtracting all the quantities, it is subject to very large systematic uncertainties. So this is one methodology. Even in this difficult situation, there are more or less robust results coming from absolute photometry. And this is spectral intensity versus wavelength. We see here the optical peak. This is the infrared peak. And you can see that there is a very large scatter of the data. There is no data here in the middle here because zodiacal light is even brighter than other wavelength. And it is very difficult to measure the EBL here. Okay, so there is this other methodology that is known as galaxy counts. What you do is to take data from very big galaxy surveys. So you take a region of the sky. Typically, these regions are very small, but you try to go as deep as possible. So you can image this region of the sky with different photometric bands. So, for instance, let's focus on this in the K band, and you can see how here they start to converge up to a certain number. So when you integrate this curve, you get how much bright is that region of the sky of that band given the source population that is making it in your detector. Okay? So in this way, you can get a good estimate of the light that is in the universe due to the populations that you are seeing. However, there are some caveats because first, you can be missing a significant amount of light coming from faint galaxies that don't make it in your survey. And second, you are subject to cosmic variance because these fields are really small, and for some reason they can be special relative to other fields. So this is a compilation of galaxy count data in comparison with the direct detection data, and you can see that they converge with the lower intensity data from absolute photometry. Okay, so that's one little conclusion. So there is another third methodology to estimate the EBL, that is making empirical models. So these empirical models allow you not only to estimate the local EBL as the previous two methods, but also its evolution over redshift. So there is a whole industry of making models of the EBL, but I usually classify them in two big categories, theoretical and observational. And in the observational models, you have those that are based on indirect observations. These are based on measurements of the cosmic star formation rate history of the universe, and you convert that production of stellar mass into light by using stellar population synthesis models. Then you have those that are based on direct galaxy observations. What I call direct galaxy observations are luminosity functions. Okay, these there are models that are older, and they are based only on local luminosity functions, and they extrapolate them backwards in time. And also more recent models that use galaxy luminosity functions measured over a wide range of redshift. So this is a compilation of models. Essentially, this is the state of the art. And you can see that most of the models, at least in the optical peak, they converge at least by within a factor of 2. The situation is much more complicated in the infrared, and the reason is because there are not many models that use infrared data in a robust way. Okay, so this is the image of the spectral energy distribution of the EBL in the local universe. What's happening at higher redshift? So at higher redshift, the models completely diverge between them. So the situation is terrible. You can see that by redshift of 2, the models diverge by a factor of 10, and the situation is just we don't know anything at redshift of 3. Okay. So there are two problems with current models, the far IR and the evolution. So to fix these problems, we try to make a new model that it was published by Monthly Notices, I think it was last month or in August, where we have used about 150 galaxies from the CANDLES survey, observed up to redshift of 6, and using the 5 CANDLES fields. So this helps in reducing cosmic variance. And this is just a plot showing the counts at this age band. And what we have done is to, using all the multi-wavelength coverage that CANDLES give us, that is excellent. It is really an unprecedented database. We have fit spectral energy distribution templates to all these galaxies. And very importantly, we have infrared information for all these galaxies. Of course, we don't have detection for all of them, but at least we have an upper limit. So we have developed a method based on some scaling relationships that we have been finding in the literature to assign some infrared flags for those galaxies where we only have upper limits by seeing how much light is absorbed in the UV and re-emitted towards the infrared. So all the details are in the paper, and we have been really careful in making completeness corrections and making sure that we calculate the infrared as precisely as it is possible. So after we have the LCD for all the galaxies, we can just adapt the templates, and we know how much light there is in the survey. Okay, so we can calculate luminosity densities at any band that we want, and integrating all that luminosity density over wavelength and over redshift, we can calculate the spectral energy distribution of the EBL. This is our result, this blue region. And we see that in the infrared, the result is between the higher previous EBL models and the lower intensity previous EBL models. Okay, so it is something in the middle. And we have been able to calculate the evolution with data of the EBL up to redshift of 6. Okay, so I show you that we can measure the EBL using absolute photometry, galaxy currents, and making models. So there is a fourth methodology, and this is what I'm going to focus my talk for the rest of the time. And this other methodology is based on an effect that is known as gamma-ray attenuation, and it is produced by gamma-ray photons that comes from cosmological distances, and they cross the EBL density on their way to Earth. So there is this effect known as pair production that makes the gamma-ray photon interact. There is some probability of interaction with the EBL photon. Okay, so producing an electron and a positron. So the net effect is that the gamma-ray photon fluxes that we detect with our instruments are attenuated relative to what we would observe if there were no EBL. This is what we know as intrinsic spectrum. This is the analytical, it is exactly what I just said, but analytically. So this is the intrinsic spectrum, this is the observed spectrum of the source, and it is attenuated by an exponential that is dependent on a parameter tau. That tau is the optical depth, and it is dependent on the energy of the gamma-ray photon and the redshift to the source. So this is the integral of how we calculate tau. It might look like a complicated equation, but it is actually not. It is just a standard optical depth where you have a term that is dependent on the distance that is crossed by the photon. You have here a term that tells you about the cross-section of the interaction, in our case, the pair production. And this is a government term dependent on the density of the medium. The density of the medium is the EBL photon density in our case. So this is an example of how tau looks like. So you have an idea. This is this effect starts happening for gamma-ray photons of about 30 GeVs or so. That is when there is enough energy to pair produce with the EBL photon. Okay, so these functions are usually well, they are monotonically increasing. They increase monotonically with the energy, and the higher the redshift, the higher tau. Okay, so this tau is for a low redshift, and this one for a high redshift. This is just the exponential of minus tau. Okay, the attenuation factor. Okay, so how do we measure gamma-ray photons? How do we astronomers measure gamma-ray photons? We have the Fermi satellite in space that is an all-sky instrument. It scans the sky almost regularly over some times, and the energy sensitivity is the photon energy sensitivity is about between 100 MeV and a few hundred GeV. The peak of the sensitivity is around 1 GeV. So Fermi mainly produced a picture of the sky at about 1 GeV. I will tell you a bit later more about Fermi. And then we also have the IACTS. These are the Imaging Atmospheric Cherenkov Telescopes. These are instruments that are characterized by very small field of view, but they have very high sensitivity at the TeV range. So the most active collaborations are Veritas, HEST, and MAGIC, that you probably are all familiar with it. And also now we are building TTA also in La Palma, and TTA South will be also built in Chile soon. But you may wonder, how are we detecting gamma ray photons from Earth? If the atmosphere is, of course, opaque to these very high energetic photons. So we take advantage of an effect that is known as Cherenkov light. It is that when a primary particle enters the atmosphere, this primary particle can be a gamma ray photon or a cosmic ray, they interact with the atmosphere, producing a cascade of photons, because when a particle crosses medium at a velocity higher than the speed of light in that medium, this Cherenkov effect is produced. Okay, and it is a bluish light, so the Cherenkov detectors essentially are telescopes that are sensitive to blue light. They image the shower that is produced in the atmosphere, and they characterize it in three ways. They characterize the intensity of the shower, that is related with the energy of the primary particle. They also see the shape that was produced in the camera, that is related with the nature of the particle, either a photon or a cosmic ray. And then also the direction tells you about where the primary particle is coming from. If you put together several telescopes using stereoscopic observations, you get a much better representation of the shower, and therefore you can derive the characteristic of the primary particle much better than with one single telescope. So this is a representation, an artistic representation of how we expect TTA South to be in the southern hemisphere. And this is a real picture of the first telescope of TTA North in La Palma, known as a large size telescope. Okay, this is the LST. And this is the counting house. MAGIC are around here, you probably all know. So let me tell you a few more words about Fermi. It was launched in the year 2008, and it contains three different main instruments. One is a tracking system, a calorimeter, and an anti-coincidence detector. This is for the main instrument in Fermi, that is the Large Area Telescope. It has actually two. Fermi has two instruments. I'm going to tell you only about the LAT. And this is more as a particle detector rather than a telescope, because it works exactly in that way. It converts an incident gamma ray to an electron-positron pair to construct the gamma ray direction from the tracks in the pair, and the calorimeter measures the photon energy, and the anti-coincidence detector limits the background. So it has a very wide field of view, so it allows for scanning the whole sky regularly, and it has a very large effective area and low dead time for getting for measuring the photons. So this is the image of the gamma ray sky that we had in the year 2000 by EGRETS. It was the predecessor of Fermi. You can see that it made an excellent work, but it was very difficult to resolve sources, and there was no very good quality. So going to the image that we have now from Fermi, you can see that it really has has produced a breakthrough in the understanding of gamma ray, of the gamma ray sky. You can clearly see thousands of point sources. You see prominent diffuse emission. You can really resolve some structures and extensions for some sources. So really, Fermi has produced an awesome amount of high quality data. So just let me tell you a few more words about what Fermi is producing, and then I come back to the science. So Fermi has released a few source catalogs. One of them was the 3FGL that was built with 4 years of data. Then we did the FHA catalogs. These catalogs were focused on squeezing the energies, the higher energies with Fermi, thinking in trying to close the gap with the energies that are accessible to the Cherenkov telescope. Okay, essentially this was done with the 2FHL that was built with photons with energies higher than 50 GeV. That is exactly at those energies when the Cherenkov telescopes start to detect photons. And then we have the last release of the catalog, that is the 4FEL, that is the broadband, let's say, high energy, sorry, the broadband, the broad coverage of the energy range. Okay. Okay, so coming back to what we want to do, I was telling you that there are extragalactic sources that emit gamma-ray photons, and those gamma-ray photons are attenuated by EBL interaction. So those objects typically are blazars. The gamma-ray sky is completely dominated by this type of sources. Blazars are AGNs that have are launching jets. And those jets just happen to be looking in our direction. Okay, so the jets are pointing exactly toward us. This is the typical SED of some blazars. There are different types of these objects. As examples, you can see that they, but in general, they typically have this double peak shape where this lower energy peak is produced by cyclotron radiation, and the higher energy peak can be, in many cases, produced by inverse contact, okay? But what I want to show you is that Fermi typically sees this region, okay? And the Cherenkov telescope typically see how the spectrum is coming down. Okay, so this is what we did to measure the EBL using this technique. We use 9 years of Fermi data. This is the sky map showing all the blazars that we are using in our sample. The sample goes from the very local universe up to redshift of 3, but we also include 1 GRB in our sample at redshift of 4.3. It is the most luminous GRB ever detected by Fermi. So in a few words, the methodology, since we can take advantage that Fermi covers a broad energy range, there is a lower energy part that is not attenuated by the EBL, and there is a higher energy part that is indeed attenuated by the EBL. So what we do is statistically extrapolate the lower energy parts towards the higher energy parts. This is what we call the intrinsic spectrum, and compare using some likelihood with the data. Okay, we don't do this in the whole energy range. We do it in a smaller energy range, and we have tested the methodology that there is really no systematics that are introduced by using this methodology, statistically speaking. So I'm not gonna focus more on the methodology because I want to show you the results, and let's go for this. So this methodology was actually pioneered in the year 2012 by also the Fermi collaboration in a science paper. We could do this in 3 different energy redshift ranges, but they were very wide. Okay, so we could only claim the detection of the EBL, but we couldn't characterize the shape of the EBL. That is what we are doing actually in the new work. So we went from this detection to this characterization. We measured the tau, the optical depth, in 12 redshift beams. They are much smaller than before, and also in several energy ranges. So we can characterize this optical depth much better. Since we have measured this optical depth up to redshift of 3 in a broad energy range, we can from here estimate a very interesting quantity that is known as the cosmic gamma-ray horizon. What is this? So in this plot, you show energy versus redshift, and you plot all the highest energy photons that you detect with Fermi from Blazars. You make this type of plot, and you can see that there is some kind of frontier here. You are not detecting 1 TeV photons coming from redshift of 2, and this is because of EBL attenuation. Okay, so this kind of frontier is what we know as the cosmic gamma-ray horizon that divides the universe between this transparent region and this opaque region. Okay, it hasn't been measured before, at least in a good way. So the proper definition of the cosmic gamma-ray horizon is those energies at which the optical depth becomes the unity for a given redshift. So we can extract from here exactly that definition, the energy at which the optical depth becomes 1, okay, for the 12 redshift beams. And in this way, we measure the cosmic gamma-ray horizon. We compare the cosmic gamma-ray horizon with those that are derived from the EBL models. And we see that actually the EBL models were doing pretty well, and they are very much compatible. So something that is completely new in this work is that from the measurement of the optical depth, we want now to convert and try to see if we can say some information about the spectral energy distribution of the EBL. Okay? So this can be done. Remember that in the equation of tau, we had the term of the distance, the cross-section, and also the density of the EBL. Okay? It was this term. And this term can be written as a function of the local of the luminosity densities. Okay, galaxy luminosity densities. So we can now write the galaxy luminosity densities as the evolution of a sum of log-normal distributions that can evolve independently. This equation is exact. There is a little approximation here that we have done, but we have with simulation estimated that this approximation doesn't introduce any bias in the final result. So now it is easy from using this equation in the integral of tau, since we know tau, we can see using a likelihood analysis what luminosity densities are compatible with the optical depth that we measure from Blazars. So this gives us all these UV, optical, and near-infrared luminosity that are calculated up to redshift of 5. Okay, so this is important. We are estimating the light in the universe. We are deriving galaxy luminosity functions. Galaxy luminosity densities that are typically derived from galaxy surveys in a completely independent way. So we are not using absolutely any galaxy measurement here. The only thing we are doing is to measure the optical depth in the gamma ray spectra of Blazars. Okay, so this is an independent method. And since we know all the luminosity densities, we can integrate them and build again the EBL spectral energy distribution that is shown here. So this is our result. This is the EBL that we measure from the attenuation of Blazars. Okay, you can see that our result stop here at about 2-3 microns, because Fermi is not sensitive to the much higher energy photons that are necessary to constrain this higher wavelength region. Okay? So we can calculate the EBL in the local universe, but of course we can calculate also its evolution using our methodology. And this is the very first determination of the evolution of the EBL using gamma-ray attenuation. So we can also compare UV light, as astronomers do, to star formation rates using initial mass functions and some average galaxy estimates. So this is the so-called model plot, where you see how the mass is being built up in the universe from the early times up to now. Our results are these shade regions, and these are the results from galaxy surveys, from measuring these line and break galaxies. So again, I really want to emphasize that our result is not using any galaxy measurement. This is completely independent of everything that has been done in the past, and the results converge and agree really well. We can even constrain the star formation rate density of the universe at redshift of 6. That is a region where we are going to have to wait till the new James Webb telescope to constrain these early galaxies. So this is the plot that I showed you before of tau from Fermi, but we also have measured the taus combining in our methodology, in another word, combining data from Cherenkov telescopes in the clean. So we have been able to measure tau in this other much, you can see here, higher energies than here, using again this Cherenkov data. So combining all this, we found the spectral energy distribution of the EBL up to wavelength of about 100. This is really nice and a very complete representation of the EBL extracted from a pretty homogeneous data. So I'm going to skip this, and let me just finish with another work that we have done, trying to see if we can shed some light on this problem that the also called tension in the H0 parameter. Okay, so there are some works that are measuring the Hubble constant in this lower range of about 68, and there are another set of methodologies that are measuring a higher Hubble parameter. So there is this so-called tension that some people claim to be at 5 sigma, essentially, of significance. So let's see if we can use our methodology to give also a value of H0. So remember that tau is dependent on the distance, the cross-section of the per production, interaction, and also on the EBL photon density evolution. And you can see that cosmology is actually included here in this term, and also here in the EBL photon density evolution. Okay, so we can think of a likelihood analysis where our free parameter is H0 here and here, and see what H0 represents better the optical depth that we measured from the gamma-ray data. So we have done this for 2 different EBL models, because it is absolutely necessary here to assume a template, to assume a shape of the EBL for doing this. Okay, so we have done this for 2 different models. Finke 10 and Dominguez 11, and we have combined the result of both from both models to somehow have an estimate of the systematic uncertainty from introducing or from fixing a given EBL model. Okay, so finally, this is the likelihood that we have found, the probability density distribution, and we have found a value for H0 of about 66 in standard units, which put us in this lower energy, in this lower H0 value of the cloud of results. So finishing, let me tell you some words about what we are doing now for the future. So now we want, with the new EBL model that I introduced you at the beginning of the talk, we want to estimate the cosmic gamma-ray horizon from the new model, where we take and consider all the uncertainties in the model in a proper way. And we also are trying to explore a bit more on this H0 value. We are now trying to see if we can help to resolve this discrepancy. And we have done our analysis using what we call the high redshift sample. These are Blazars only at the higher redshift. We are using redshift higher than 0.6 for here, and here using our low redshift sample. And it is interesting that there is this divergence in the values of H0, but this is something really new that we are exploring, trying to see where this discrepancy is coming. So these are my conclusions. I have presented you a new empirical EBL model based on data up to the redshift of 6 in the 5 candle fields, a very significant detection and characterization of the EBL attenuation up to redshift of 3. We have presented the most complete derivation so far of the local EBL and its evolution over redshift from Fermi-LAT and Cherenkov Blazar data combined. And we have derived the cosmic star formation rate density up to redshift of 6, that is unbiased from different galaxy surveys in completeness. And also, I have presented a cosmological measurement of H0. We have in the paper also constrained omega matter from our independent technique. So, as I said at the very beginning of the talk, I hope I have convinced you that gamma-ray astronomy has matured enough as for providing competitive measurements in galaxy evolution and also cosmology. And this is it.
Okay. So let's check if there are any questions here to the speaker in the audience. And of course, in Zoom or as well. If you're in Zoom, you may raise your hand, and I see one raised hand there. You can also write it in the chat, and we will read it or speak them up. So let's see. Let's start with questions in the audience, maybe, and I see Ignacio Pamuti also raised the hand. So, so where is your the state of yesterday here with facing primarily that is focused on like what kind of sources do you focus?
Actually, I don't think there is any constraint in that sense, because we have shown in the so before we thought that only DLX could give us a good estimate of the EBL because we understood better the spectral behavior. But in the last paper, we showed that we can also use the spectral quasars for this goal. So I don't think we have any special type of source that we should focus. Was this your question?
And also the difference, like so we focus on close sources or far away sources.
For this, you mean for the EBL or for the H0 measure? For the EBL, we should focus on everything. I think if we want to measure the evolution, so the higher we go in redshift, the better we will constrain the redshift evolution of the EBL. That is actually a pretty hot topic.
Well, thanks for the talk. Very interesting. Many questions. I'm sure that most because I'm not part of the to this thing. But I have two short questions. So the first one is, when you never go below 1,000 angstrom, when you can constrain the spectrum below that, which is really, if you're thinking about the organization of the data, this is one. And the other one is about how you go from the EBL to the cosmic star formation rate density, which is dependent, and these are still model dependent. Different combinations of galaxy populations, different extinctions, and so on and so forth. So it's a non-trivial, I understand. It's not really way.
Okay, so relative to the first question, actually the density of photons quickly decrease below 1,000 amps. So there is no attenuation at all produced with gamma-ray photons with those UV photons. So that's why we don't see them with this technique.
But this gap, I mean, these are the photons.
Yeah, you don't have density enough of these UV photons to pair produce with the gamma-ray photons. So the pair production is not happening.
So the cross section is not enough.
Exactly. The cross section. Well, it is not the cross section. It is. Remember. You have here the density of the EBL photons. This term at those wavelengths, it is really low. So yeah, it is a combination of the pair production of the cross section with the density. It just doesn't happen. There is no probability that a gamma-ray photon interact with UV photons of less than 1,000. It's not happening. Your second question was about the EBL. Yeah. So we do essentially what astronomers typically do. They assume they convert from UV light to star formation rate using assuming an initial mass function and some average galaxy extinction. This is what they usually do. They convert the UV luminosity densities to a star formation, right? There are some.
That's for galaxies. So you go to a galaxy, you measure the exact star formation rate. So, and we're using the background and applying the same. So I don't know what to say.
Yeah, but we are essentially measuring the luminosity densities in the UV.
That's the luminosity. It's not the luminosity of the star formation rate.
Yeah, but that's coming from the galaxy population. You can extract it from there. It is the same thing. It is the same in the second methodology that I showed you, the galaxy count. You measure galaxy count, you see the galaxy population.
Part of this focus absorb. So you go to the galaxy, you want to do things
yeah, but these are really
all the dust, all the galaxies. So these before.
Yeah, but I think that's considered here in this galaxy, in this term. Okay, is correct.
Maybe to continue with further questions here. We have one remote one by Ignacio Trujillo. Ignacio, please try to speak up and let's see if you can hear
me.
Hear me very well, yes.
Okay. Yeah, my question, Alberto, is related to one of your final slides about measuring the Hubble constant using different redshifts of light. Here, remotely we couldn't see what you find because the screen is not visible. So can you tell us by word what are the findings you have for the Hubble constant depending on the redshift line?
Yeah, so what we are actually constraining here is omega matter in the y-axis. and H0 in the x-axis. We are here simultaneously trying to give a value for H0 and omega matter. And what we see here is that we are finding a very low value for omega matter in our standard work, let's say, and we want to see why this is happening. And it seems that it is there is a discrepancy between the result that this high redshift sample is giving relative to the results that the low redshift sample is giving.
Okay, so can you tell us the difference in the Hubble constant depending on the redshift?
No. This is related with the discrepancy in omega matter. Sorry,
okay.
I didn't say it very clearly. You are right. But this is more caring about this very low omega matter value that we are finding. So we are finding,
You said that the Hubble constant you measure was I mean, when you say the value you get is around 68, you said
66, I think.
66,
yes.
Sorry. So this is closer to the let's say the cosmological value.
Yes, that's correct.
What is the typical redshift of your sources? So the main contributor to this value?
Yeah, the peak, I think it is at around redshift of 1.
Okay.
Yeah.
So then it's fine. So it's you are okay with what the cosmology says. So the discrepancy starts quite closer to us. So.
Yeah.
Okay, thank you.
Yeah.
Thank you. Yeah. Then, Ignacio, any other questions either from the audience or from the remote listeners? One more.
Are those high redshift and low redshift samples different in terms of what kind of sources they have? Like, for
Please speak loud so they can hear the remote. So that
does this high redshift sample include more FSRQs, for instance, than the low redshift sample?
So I'm going to repeat the question for the case. So she's asking if the high redshift sample and low redshift sample in this case are contains a different Blazar population, no? Essentially. So probably yes, because flat spectrum radio quasars tend to be found at higher redshift. So probably the ratio of BLR and flat spectrum radio quasars are different for these two samples. But I didn't check it carefully. This really is, I just show it to you as a to-do thing. So we are still exploring the details of this. We are actively trying to working on this topic.
Okay, I think we have no further questions neither in the chat, neither the audience. So let's thank the speaker once more.